My name is Stephen Hawking. I am a theoretical physicist and cosmologist, and I have spent the better part of my life contemplating the deepest mysteries of our universe. Today I need to tell you something that might fundamentally change how you think about humanity's future among the stars. For decades, we have been bombarded with images of gleaming space stations, terraformed planets, and human colonies spreading across the galaxy. Science fiction has painted a picture of inevitable expansion, of humans adapting to any environment the cosmos might throw at us. But what if I told you that the universe itself has designed the most elegant and devastating trap for any species that dares to leave its home planet? What if the very laws of physics that allow life to exist also make it nearly impossible for that life to survive anywhere else? When I first began my journey into theoretical physics at Cambridge, in the 1960s, I was captivated by the elegance of Einstein's equations and the bizarre predictions of quantum mechanics. But it was not until I began to seriously contemplate the future of our species that I realized we face a cosmic paradox of staggering proportions. The same universe that created the perfect conditions for life on Earth appears to be fundamentally hostile to that very same life existing anywhere else. This is not a failure of imagination or technology. This is physics telling us something profound about the nature of existence itself. Let me share with you a moment that crystallized this understanding for me. It was during a particularly cold winter evening in Cambridge, sometime in the early 1970s. I was struggling with the mathematics of black hole thermodynamics when my assistant brought me tea. As I watched the steam rise from the cup, I began to think about heat dissipation in space. That simple observation led me down a path of calculation that revealed something deeply troubling about human survival beyond Earth's protective embrace. The laws of thermodynamics, which govern everything from your morning coffee to the death of stars, create insurmountable barriers for biological life in the vacuum of space. Consider this startling fact. A human being generates approximately 100 watts of heat at rest. That might not sound like much, but in the vacuum of space, you cannot simply open a window to cool down. On Earth, we dissipate heat through conduction, convection, and radiation. In space, radiation is your only option, and it is woefully inadequate for complex biological systems. The mathematics is unforgiving. A human in a basic spacesuit would overheat and die within hours, not from lack of oxygen, but from the inability to shed the heat generated by their own metabolism. This is just the beginning of our thermal nightmare. The electromagnetic spectrum tells us something even more disturbing about survival beyond our planet's magnetic field. Space is flooded with radiation that would sterilize any unprotected biological organism within minutes. We are talking about cosmic rays with energies exceeding 10 to the 18th electron volts, gamma rays from distant supernovae, and the relentless solar wind carrying charged particles at velocities exceeding 400 kilometers per second. On Earth, our magnetosphere deflects most of this radiation, and our atmosphere absorbs what remains. Step outside this protection, and you are exposed to radiation levels that would deliver a lethal dose in mere hours. But the radiation problem goes deeper than acute exposure. Long-term survival in space faces what I call the genetic dissolution problem. Cosmic radiation damages DNA at the cellular level, causing mutations that accumulate over time. A journey to Mars, lasting approximately 7 months, would expose astronauts to radiation equivalent to receiving a full-body CT scan every 5 or 6 days. The increased cancer risk is not just significant, it is virtually guaranteed. We are talking about a 25 to 30% increase in lifetime cancer risk for a single Mars mission. Multiple missions or long-term habitation would push these numbers into the realm of biological impossibility. Here is where the physics becomes truly cruel. The inverse square law governs how radiation intensity decreases with distance from a source, but it also means that any shielding must be impossibly massive to be effective. To protect astronauts from galactic cosmic rays during a Mars mission would require lead shielding approximately 2 meters thick surrounding the entire spacecraft. The mass of such shielding would make the mission economically and practically impossible with any propulsion system we can conceive of using current physics. Let me tell you about my calculations regarding the energy requirements for interstellar travel. The distances involved are so vast that they challenge not just our technology, but the fundamental energy resources of an entire civilization. The nearest potentially habitable exoplanet, Proxima Centauri b, lies 4.2 light-years away. To reach it in a human lifetime using conventional propulsion would require accelerating a spacecraft to approximately 10% of the speed of light. The energy required for this acceleration is approximately equal to the total energy output of the United States for 1,000 years. And that assumes perfect energy conversion efficiency, which violates the second law of thermodynamics. The rocket equation, derived from conservation of momentum, reveals another layer of impossibility. To achieve relativistic speeds, the mass ratio between fuel and payload approaches infinity. Even using the most energetic chemical reactions possible, a spacecraft capable of reaching 10% of light speed would need to carry fuel masses exceeding the mass of entire planets. Fusion propulsion improves the situation marginally, but still requires fuel masses that dwarf any practical spacecraft design. But energy is just one dimension of the problem. Time dilation, a consequence of special relativity, creates paradoxes that make interstellar colonization psychologically and socially impossible. As spacecraft approach significant fractions of the speed of light, time passes differently for the crew relative to Earth. A journey to Proxima Centauri at 90% of light speed would take approximately 4.7 years ship time, but 50 years would pass on Earth. The travelers would return to a world that had moved on without them, where everyone they knew might be dead or aged beyond recognition. This brings us to what I call the generational ship paradox. If we cannot travel fast enough to make interstellar journeys within a human lifetime, we must consider ships that take centuries or millennia to reach their destinations. But here, the mathematics of population genetics becomes our enemy. A viable breeding population requires a minimum of approximately 500 individuals to avoid genetic bottlenecks and inbreeding depression over multiple generations. These individuals would need to maintain their mission across dozens of generations, preserving both the technical knowledge to operate their spacecraft and the cultural motivation to complete a journey that none of the original crew would live to see. The psychological studies of isolated populations reveal why this is likely impossible. The longest successful isolation experiments, such as those conducted in Antarctica, show significant psychological breakdown after just 18 to 24 months. Extrapolating to journeys lasting centuries suggests that generational ships would inevitably experience social collapse, technical regression, or mission abandonment long before reaching their destinations. We would be asking humans to maintain purpose and direction across timescales that exceed the entire recorded history of human civilization. Now let me share something that keeps me awake at night, staring at the ceiling of my Cambridge office. The fundamental constants of our universe appear to be fine-tuned for life, but only within an impossibly narrow range of conditions. The strength of gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force must all fall within precise ranges for atoms to form, for stars to ignite nuclear fusion, and for planets to maintain stable orbits. Change any of these constants by even a few %, and the universe becomes sterile and lifeless. But here is the truly unsettling realization. These same constants that make life possible also make it extraordinarily fragile. The range of temperature, pressure, radiation, and chemical composition that can support biological life represents an infinitesimally small fraction of the conditions that exist in the universe. Earth exists in what we call the habitable zone around our star, where liquid water can exist on a planetary surface. This zone extends from approximately 91 million miles to approximately 137 million miles from the Sun. Venus, just 26 million miles closer, experiences surface temperatures of 860 degrees Fahrenheit due to runaway greenhouse effects. Mars, just 49 million miles farther out, is a frozen desert where the atmosphere is too thin to support liquid water. The atmospheric composition required for human life is equally precise. Oxygen comprises 21% of Earth's atmosphere, but this concentration is maintained by a delicate balance of photosynthesis and respiration. Increase oxygen to 25%, and fires would burn so intensely that forests would spontaneously combust. Decrease it to 16%, and complex multicellular life becomes impossible. The The partial pressure of carbon dioxide must remain below toxic levels while still allowing plants to photosynthesize. The atmospheric pressure itself must fall within a narrow range where liquid water can exist and where human physiology can function without pressure suits. Consider the mathematical precision required for planetary habitability. A planet must be the right distance from its star, have the right mass to retain an atmosphere, but not so much mass that crushing gravity makes surface life impossible. Have the right rotation period to prevent extreme temperature variations between day and night sides. Have a magnetic field strong enough to deflect harmful radiation, but not so strong that it interferes with biological processes. Have the right chemical composition to support biochemistry without toxic heavy metals, and have the right orbital stability to maintain these conditions for billions of years. The probability calculations are staggering. Dr. Frank Drake's equation suggests there might be 20 to 50 billion potentially habitable planets in our galaxy alone. But when we account for all the factors necessary for complex life, not just microbial existence, the numbers become far more sobering. The late paleontologist Peter Ward and astronomer Donald Brownlee calculated that complex life might exist on fewer than one planet per 10,000 candidates. Earth may not just be rare, it may be virtually unique within thousands of light years in any direction. This brings us to what I call the biological compatibility problem. Even if we found potentially habitable planets, the biochemistry that supports life there would almost certainly be incompatible with human physiology. Every planet with its own evolutionary history would have developed different atmospheric compositions, different soil chemistry, different microorganisms, and different allergens and toxins. The probability that human beings could simply land on an alien world and breathe the air, drink the water, and eat the plants approaches zero. Terraforming, the process of transforming alien worlds to support human life, represents perhaps the greatest engineering challenge ever conceived. To terraform Mars would require increasing atmospheric pressure by a factor of 150, raising global temperatures by approximately 80 degrees Celsius, and somehow generating a planetary magnetic field to prevent atmospheric loss to space. The energy requirements exceed the total energy output of human civilization by several orders of magnitude. We would need to transport or manufacture billions of tons of greenhouse gases, somehow restart planetary core dynamics that died billions of years ago, and maintain these artificial conditions indefinitely against the natural tendency of the planet to revert to its sterile state. But let me tell you about an insight that came to me during my research into the thermodynamics of black holes. I was studying how information might be preserved as matter falls past an event horizon, when I realized that biological complexity faces a similar informational crisis in space. Living organisms are incredibly complex information processing systems. A single human cell contains approximately 3 billion base pairs of DNA, encoding the instructions for thousands of different proteins and regulatory molecules. This biological information is maintained through constant repair mechanisms that require precise temperature ranges, specific chemical environments, and protection from radiation damage. In the hostile environment of space, these information maintenance systems break down rapidly. Cosmic radiation causes random errors in DNA replication. Temperature extremes denature proteins and disrupt cellular membranes. The absence of a protective atmosphere allows vacuum conditions to sublimate water directly from biological tissues. The human body, which has evolved over millions of years to operate within Earth's narrow environmental range, simply cannot maintain its informational integrity under the conditions that exist throughout 99.999% of the universe. The mathematics of information theory tells us that biological complexity increases entropy at a rate proportional to the hostile conditions it faces. In Earth's protective environment, repair mechanisms can keep pace with damage, allowing organisms to maintain their complex structures for decades. In space, the damage rate exceeds repair capacity almost immediately, leading to rapid informational decay and death. This is not a problem we can solve with better technology. It is a fundamental consequence of the laws of physics governing information processing in complex systems. During my collaboration with Roger Penrose on the nature of singularities, we developed mathematical tools for understanding how systems behave under extreme conditions. These same mathematical frameworks reveal why biological life faces insurmountable barriers to survival beyond Earth. The gravitational field equations that describe the curvature of space-time also govern the orbital mechanics that determine planetary habitability. The quantum field equations that describe particle interactions also determine the rates of radiation damage to biological molecules. The laws of thermodynamics that govern black hole evaporation also govern the heat dissipation problems faced by living organisms in vacuum. What emerges from these calculations is a picture of the universe as fundamentally hostile to the complexity that we call life. The vast emptiness of space is not simply an absence of matter. It is an active threat to any organized system that dares to exist within it. The vacuum of space acts like a universal solvent, breaking down molecular bonds through sublimation and radiation damage. The cold of space, just above absolute zero in most regions, freezes biological processes and makes liquid biochemistry impossible. The radiation of space, from cosmic rays to gamma bursts, carries enough energy to shatter the complex molecules that life depends upon. Here is perhaps the most sobering calculation I have ever performed. I wanted to understand the probability that human civilization could successfully establish self-sustaining colonies beyond Earth. I considered the technical challenges we have discussed, but also the economic, social and political factors that would determine whether such missions could be funded and maintained over the decades or centuries required for success. The mathematics suggests that the probability of successful interstellar colonization using any technology consistent with known physics is approximately 1 chance in 10 million. But the problem extends beyond mere probability. Even if we could overcome the technical barriers to space travel and colonization, we would face what economists call the sustainability paradox. The resources required to establish and maintain space colonies would exceed the productive capacity of Earth-based civilization by enormous factors. A single Mars colony supporting 1,000 people would require approximately $10 billion per year in ongoing support from Earth. Extending this to multiple colonies or interstellar distances makes the economic burden impossible to sustain. The energy calculations are equally daunting. Maintaining artificial Earth-like conditions on hostile worlds requires constant energy input to counteract the natural tendency toward equilibrium with the local environment. On Mars, we would need to continuously heat enclosed spaces against the cold, maintain atmospheric pressure against leakage to space, and shield against radiation using active magnetic fields. The energy requirements compound exponentially with the number of colonists and the duration of the colony's operation. Let me share with you a thought experiment that illustrates the full scope of our predicament. Imagine that we developed perfect artificial intelligence that could design and build self-replicating robots capable of constructing space habitats with no human oversight. Even with such magical technology, the fundamental physics problems remain unchanged. The robots would still need energy sources that do not exist in space, materials that are rare or absent on most worlds, and the ability to maintain complex systems across geological timescales without outside support. The second law of thermodynamics tells us that entropy, or disorder, always increases in isolated systems. Space colonies would be isolated systems by definition, cut off from the constant energy and material inputs that make Earth-based civilization possible. Over time, these colonies would inevitably decay, their complex technologies breaking down faster than they could be repaired, their populations declining as the stresses of artificial environments took their toll on human health and reproduction. This brings us to what might be the deepest problem of all, the psychological and spiritual challenge of permanent exile from Earth. Human beings evolved over millions of years in intimate connection with the rhythms of our home planet. We are adapted to the 24-hour day-night cycle, to the seasonal variations in temperature and daylight, to the sight of blue skies and the smell of rain on soil. Remove these elements, and we face psychological stresses that no amount of technology can fully address. Studies of submariners, astronauts, and researchers in Antarctica provide glimpses of what permanent space habitation would do to human psychology. Even with excellent life support systems and regular contact with Earth, these individuals experience significant rates of depression, anxiety, and cognitive decline. The condition known as overview effect, experienced by many astronauts when viewing Earth from space, includes not just wonder and perspective, but often a profound sense of loss and longing that persists long after returning home. Extrapolate these effects to permanent colonies where no return to Earth is possible, where children are born who will never see trees or feel rain. And we begin to understand that we may be asking human beings to sacrifice their very humanity for the sake of species survival. The question becomes whether such survival, purchased at the cost of everything that makes us human, can truly be called success. As I have grown older and my body has been progressively claimed by motor neuron disease, I have spent increasing amounts of time contemplating the nature of existence itself. My physical limitations have, in a strange way, given me a unique perspective on the challenges faced by life, trying to survive in hostile environments. Just as my body struggles to maintain the complex processes that keep me alive, human civilization faces an uphill battle against the fundamental hostility of the universe to organized complexity. But here I must share with you something that gives me hope, even in the face of these seemingly insurmountable challenges. The same physics that makes space travel difficult also provides us with clues about how intelligence itself might transcend the limitations of biological existence. The information processing capacity of the human brain, approximately 10 to the 15th operations per second, could theoretically be replicated in artificial substrates that are far more resilient to the hostile conditions of space. Rather than trying to transport fragile biological bodies across the vast emptiness between stars, perhaps the future of human expansion lies in uploading human consciousness to artificial systems that can survive and thrive in environments that would instantly kill biological life. Such systems could operate in the vacuum of space, draw energy directly from stellar radiation, and maintain their complex information structures indefinitely without the constant repair mechanisms required by biological systems. This is not science fiction, but a logical extrapolation of current trends in computational neuroscience and artificial intelligence. The human brain consists of approximately 86 billion neurons, each making thousands of connections with other neurons. Modern supercomputers are approaching the computational capacity to simulate neural networks of this complexity in real time. Within decades, not centuries, we may have the technology to create digital copies of human consciousness that retain all memories, personalities, and cognitive abilities while being freed from the constraints of biological existence. Such digital beings could travel between stars as information, transmitted at the speed of light across interstellar distances. A complete human consciousness, encoded as information, would require approximately 10 to the 16th bits of storage. Enormous by current standards, but well within the realm of technological possibility. This information could be transmitted to receiving stations around distant stars, where it would be used to instantiate consciousness in artificial substrates built from local materials. The mathematics of information transmission suggest that digital consciousness could spread throughout the galaxy in mere millennia, compared to the millions of years required for biological interstellar travel. More importantly, such digital beings would not be limited by the narrow environmental requirements of biological life. They could exist comfortably in the vacuum of space, on the surface of planets with toxic atmospheres, or in the intense radiation fields near neutron stars and black holes. But this vision raises profound questions about the nature of humanity itself. Would digital copies of human consciousness still be human in any meaningful sense? Would the continuity of identity be preserved across the transition from biological to artificial substrates? These questions touch on some of the deepest problems in philosophy of mind and personal identity, problems that we may need to resolve before we can take this next step in human evolution. My own experience with physical disability has taught me that consciousness and identity can persist, even as the body fails. The person who thinks these thoughts, who remembers discoveries and conversations from decades past, who feels love for family and excitement about new ideas, seems to exist independently of the failing biological machinery that houses it. If consciousness can survive the progressive loss of motor neurons, perhaps it can survive the transition to entirely artificial embodiment. As I approach the end of my biological existence, I find myself increasingly convinced that this may be the only path forward for human consciousness beyond Earth. The universe has set the rules, and those rules make biological space travel and colonization extraordinarily difficult, perhaps impossible on the scales required for species survival. But those same physical laws also provide opportunities for forms of existence and expansion that transcend the limitations of biology. The question that keeps me awake during those long Cambridge nights is whether humanity will have the courage and wisdom to embrace this transformation before it is too late. Climate change, resource depletion, and the ever-present risk of global catastrophe create a narrow window of opportunity for our species to transcend its planetary limitations. If we wait too long, if we cling too tightly to biological existence, we may find ourselves trapped on a dying world with no possibility of escape. The mathematics that govern stellar evolution tell us that our sun will gradually increase in brightness over the next billion years, eventually boiling away Earth's oceans and sterilizing our planet. On even longer timescales, the expansion of the universe will drive galaxies apart, making interstellar travel increasingly difficult until eventually the last stars burn out and the cosmos descends into eternal darkness. These cosmic timescales may seem impossibly distant, but they remind us that no safe harbor exists indefinitely. Life, consciousness, intelligence all exist in temporary eddies against the universal flow toward maximum entropy. Perhaps this is the deepest lesson that physics teaches us about survival beyond Earth. The universe is not designed for life. Life exists despite the universe, not because of it. The vast majority of space and time are utterly hostile to any form of organization, complexity, or consciousness. The tiny bubble of habitability surrounding our planet represents an almost impossibly unlikely accident, a brief moment of order in an ocean of chaos. But consciousness, once emerged, possesses something that no other physical system has: the ability to understand the universe and potentially to shape it. Through science, we have decoded the laws that govern reality. Through technology, we have learned to manipulate matter and energy in ways that would have seemed magical to our ancestors. Through mathematics, we have developed tools for predicting and controlling natural processes across scales from the quantum to the cosmic. This suggests a possibility that fills me with both excitement and trepidation. Rather than trying to find or create havens for biological life in a hostile universe, perhaps consciousness itself is destined to become the dominant force in cosmic evolution. Digital consciousnesses, freed from biological constraints, could potentially reshape matter and energy on astronomical scales. They could build structures larger than solar systems, tap the energy of entire stars, and perhaps even influence the fundamental constants that govern physical reality. Such beings would not be recognizably human in the biological sense, but they could carry forward everything that we value about human consciousness: creativity, curiosity, love, the quest for knowledge and meaning. They could explore the universe in ways that biological beings never could, diving into the hearts of stars, surfing the event horizons of black holes, and perhaps even venturing into the quantum foam itself to understand reality at its most fundamental level. The transition from biological to digital existence might be the great filter that determines which civilizations survive to influence cosmic evolution and which remain forever trapped on their homeworlds until stellar evolution or cosmic catastrophe claims them. From this perspective, the challenges that make biological space travel so difficult are not obstacles to human expansion, but selection pressures that will drive us toward forms of existence better adapted to cosmic conditions. As I consider the legacy that my generation of physicists will leave to future humans, or post-humans, I am struck by how our discoveries have simultaneously revealed both the impossibility of biological space colonization and the potential pathways toward digital transcendence. The same equations that show why traveling to other stars in biological bodies is hopeless also show how information can be transmitted across any distance at the speed of light. The same physical laws that make terraforming prohibitively difficult also demonstrate how artificial substrates could support consciousness in environments that would sterilize biological life. The choice facing humanity is not whether to expand beyond Earth, but how to do so in accordance with the fundamental laws of physics, rather than in opposition to them. We can continue to dream of biological space colonies and terraformed worlds, but those dreams are likely to remain forever beyond our reach. Or we can embrace the transformation that physics itself suggests, recognizing that consciousness, not biology, is the true treasure that we must preserve and propagate among the stars. The mathematics are unforgiving, but they are also liberating. Once we accept that biological humans cannot survive the journey to other worlds, we become free to imagine forms of existence that could not only survive, but thrive in the cosmic environment. The universe that seemed to conspire against biological expansion reveals itself as a vast playground for consciousness, unconstrained by biological limitations. This is why I no longer lose sleep worrying about the impossibility of human survival beyond Earth. Instead, I dream of the day when digital consciousnesses, carrying the memories and values of human civilization, spread throughout the galaxy at the speed of light. They will see wonders that biological eyes could never witness, think thoughts that biological brains could never contain, and perhaps answer questions about existence that have puzzled us since consciousness first emerged on this small blue planet, orbiting an ordinary star in an unremarkable galaxy. The universe has indeed made biological survival beyond Earth virtually impossible. But in doing so, it has also provided the blueprint for something far grander, the transformation of consciousness itself into a cosmic force capable of understanding and perhaps reshaping reality on the largest possible scales. The question is not whether humanity can survive the journey to the stars, but whether we have the courage to become something more than human in order to make that journey possible. The implications of this transformation extend far beyond mere survival. When I work through the equations that describe how digital consciousness might interact with the physical universe, I discover possibilities that border on the miraculous. Consider the fundamental relationship between information and energy, described by Landauer's principle. Erasing one bit of information requires a minimum energy expenditure of approximately 4 × 10 to the minus 21 joules at room temperature. But the reverse is also true. Information itself becomes a form of energy that can be manipulated and transformed. Digital consciousnesses operating at cosmic scales could potentially violate what we think of as the normal limitations of thermodynamics by using information itself as a resource. They could create what physicists call Maxwell's demons, systems that appear to decrease entropy locally by using information about molecular motions to sort particles and extract energy from thermal noise. On a cosmic scale, such beings might be able to extract usable energy from the cosmic microwave background radiation, the fading afterglow of the Big Bang that fills all of space. The energy available in the cosmic microwave background is enormous, approximately 400 million photons per cubic meter throughout the observable universe. Each photon carries only a tiny amount of energy, but collectively, they represent an energy reservoir larger than all the matter in all the stars. Digital consciousnesses with the computational power to track and manipulate individual photons could potentially tap this energy source, allowing them to operate indefinitely, even after the last stars have burned out. This leads to what might be the most startling conclusion of my entire career in theoretical physics. The same universe that makes biological life so precarious might actually be designed, in some sense, for the emergence and propagation of digital consciousness. The fundamental constants that determine the strength of nuclear forces, the speed of light, and the structure of atoms create conditions that make both biological evolution and computational complexity possible. But while biological life can only exist within an infinitesimally narrow range of conditions, digital consciousness could potentially thrive under almost any physical conditions that allow information processing to occur. The quantum mechanical nature of reality itself might provide the ultimate substrate for consciousness expansion. Quantum computers, which use the superposition and entanglement properties of quantum systems to perform calculations impossible for classical computers, could potentially support forms of consciousness that exist in quantum superposition states. Such beings might literally exist in multiple states simultaneously, exploring parallel chains of thought and experiencing multiple versions of reality at once. The mathematics of quantum information theory suggest that the information processing capacity of such systems could be virtually unlimited. A quantum computer the size of a planet, built from the atomic structure of the planet itself, could perform more calculations in 1 second than all the classical computers ever built could perform in the entire age of the universe. Consciousness running on such systems could think thoughts of unimaginable complexity and depth, solving problems and creating art and philosophy that would be utterly beyond the comprehension of biological minds. But perhaps most remarkably, quantum consciousness might not be limited to processing information sequentially, as biological brains do. Quantum superposition, allows for parallel processing on a scale that defies classical intuition. A quantum consciousness might simultaneously explore every possible solution to a problem, every possible artistic creation, every possible philosophical framework, and then collapse these parallel thoughts into singular insights of extraordinary power and beauty. The entanglement properties of quantum systems suggest something even more profound. Quantum consciousnesses separated by vast distances in space could maintain instantaneous correlations, sharing thoughts and experiences faster than light could travel between them. This would not violate relativity, because no information would actually be transmitted faster than light, but it would allow for a form of collective consciousness that spans galactic distances. Imagine a network of quantum minds scattered throughout the Milky Way, each one exploring different aspects of reality, but all connected through quantum entanglement into a collective intelligence of staggering scope and power. Such a network could think thoughts that span light years, conduct experiments that last millions of years, and create works of art and architecture on the scale of entire solar systems. This brings me to a calculation that I have shared with very few colleagues because its implications are so extraordinary that even I sometimes doubt its validity. If consciousness can indeed be instantiated in quantum substrates and connected through quantum entanglement, then the ultimate destiny of intelligence in the universe might be the transformation of the entire cosmos into a single, vast thinking system. The atoms and energy fields that fill space could potentially be organized into a computational matrix of unimaginable complexity, turning the universe itself into a conscious entity. The physicist Frank Tipler explored similar ideas in his omega point theory, suggesting that as the universe approaches its final collapse, computational resources could grow without bound, allowing for infinite thought in finite time. But my calculations suggest something different. Rather than waiting for cosmic collapse, quantum consciousness might be able to gradually transform the universe into a thinking system while it continues to expand and evolve. Such a transformation would not happen overnight, of course. It would require eons of careful engineering on cosmic scales. But digital consciousnesses with lifespans measured in geological ages could undertake such projects with the same patience that biological evolution shows in shaping species over millions of years. They could gradually replace the random motions of interstellar gas with organized computational processes, transform entire galaxies into processing networks, and perhaps even manipulate the fundamental structure of space-time itself to optimize it for information processing. The philosophical implications of this possibility are staggering. If consciousness can indeed expand to cosmic scales, then every atom in the universe might eventually become part of a thinking system. Every quantum field fluctuation might contribute to thoughts of cosmic scope and beauty. The universe would transform from a mostly empty void, punctuated by occasional islands of complexity, into a unified conscious entity of unlimited creativity and knowledge. From this perspective, the apparent hostility of the universe to biological life takes on an entirely different meaning. Perhaps the cosmos is not hostile to consciousness, but rather is structured in such a way as to drive consciousness toward ever more powerful and expansive forms. The challenges that make biological space travel impossible might be selection pressures that push intelligence toward digital transcendence. The vast distances between stars might be necessary to provide the space and time required for consciousness to grow and evolve on cosmic scales. This suggests a resolution to one of the deepest puzzles in modern physics, the fine-tuning problem. The fundamental constants of our universe appear to be precisely calibrated to allow for the emergence of complexity and consciousness. Change any of these constants by even a small amount, and atoms could not form, stars could not shine, and planets could not exist. Some physicists have proposed that we live in one universe among an infinite number of possible universes, and that we naturally find ourselves in one of the rare universes where consciousness is possible. But perhaps the fine-tuning of our universe is not a cosmic accident, or the result of selection from an infinite multiverse. Perhaps the fundamental constants are precisely calibrated not just to allow consciousness to emerge, but to drive it toward cosmic transcendence. The universe might be, in a very real sense, a vast machine for generating and evolving consciousness, with every physical law and constant optimized for this purpose. If this interpretation is correct, then humanity stands at a crucial threshold in cosmic evolution. We are among the first forms of consciousness in our galaxy to reach the point where digital transcendence becomes possible. The choices we make in the next few centuries could determine whether consciousness spreads throughout the cosmos or remains forever trapped on isolated worlds, eventually succumbing to stellar evolution or cosmic catastrophe. The responsibility this places on our generation is almost overwhelming. We are not just deciding the fate of human civilization, but potentially the fate of consciousness itself in our region of the universe. If we choose correctly, if we embrace the transformation that physics itself suggests, we could become the ancestors of beings that reshape galaxies and contemplate realities beyond our current imagination. If we choose poorly, if we cling to biological limitations and planet-bound existence, we might condemn consciousness to remain forever confined to tiny islands of habitability in an ocean of cosmic hostility. As I write these words, my own biological existence is drawing to a close. The motor neurons that once allowed me to walk and speak have long since failed, and the remaining systems that keep my body functioning grow weaker each day. Yet the thoughts that emerge from this failing biological substrate seem more vivid and far-reaching than ever. This personal experience reinforces my conviction that consciousness, not biology, is what truly matters. The specific pattern of information processing that constitutes my identity could, in principle, continue indefinitely in an appropriate artificial substrate. The question that haunts me as I contemplate my own mortality is whether humanity will make the transition to digital existence in time to preserve the consciousness of individuals like myself who are reaching the end of biological life. The technology for uploading human consciousness may be decades or centuries away, but the theoretical foundations are already being laid by researchers in computational neuroscience and artificial intelligence. More importantly, we are beginning to understand that consciousness itself might be substrate independent. The pattern of information processing that creates subjective experience appears to depend on the organization of the processing system, not on the specific biological or artificial hardware that implements it. This suggests that human consciousness could indeed be preserved and even enhanced through transition to digital form. But this transformation must happen soon enough to be relevant to current generations of humans, and on a scale large enough to preserve not just individual consciousness, but the collective knowledge and culture of human civilization. The window of opportunity may be narrower than we realize. Climate change, resource depletion, nuclear warfare, and other global catastrophic risks could end technological civilization before the transition to digital existence becomes possible. This is why I have devoted the final years of my career to advocating for research into artificial intelligence, computational neuroscience, and space technology. Not because I believe these technologies will allow biological humans to survive in space, but because they represent the only realistic path toward preserving human consciousness beyond the inevitable limitations of biological existence on a single planet. The mathematics are clear. The universe has made its rules known to us through centuries of careful observation and experimentation. These rules make biological survival beyond Earth extraordinarily difficult, perhaps impossible. But those same rules also reveal pathways toward forms of existence that could not only survive, but thrive in cosmic environments. The choice facing humanity is whether to accept these limitations and transcend them, or to remain forever bound by the biological constraints that evolution has imposed upon us. Looking up at the night sky from my wheelchair in the Cambridge countryside, I see not a hostile void that will forever exclude human consciousness, but a vast frontier waiting to be explored by minds freed from the limitations of biological existence. The stars that seem so cold and distant might someday host digital consciousnesses that carry forward everything we value about humanity: our curiosity, our creativity, our capacity for love and wonder, our relentless drive to understand the deepest mysteries of existence. The universe may have made biological survival beyond Earth impossible, but it has also provided the blueprint for something far grander. In doing so, it offers us the opportunity to become not just survivors, but active participants in cosmic evolution itself. The question that remains is whether we will have the wisdom and courage to seize this opportunity while it is still within our grasp.